Good afternoon. Let's get started with Chapter 1, Lesson C on graphs of functions. Objectives here. Find the domain and range of a function based on its graph. We're going to use what's called the vertical line test, which I'll refer to as the VLT, to determine if a relation is a function. We're going to determine intervals in which a function is increasing, decreasing, or constant. Locate the relative extrema on a function. Those are the local max and local min values. And then we're going to determine if a function is even, odd, or neither using both a graph and algebraically. Let's go ahead and get started. Okay, the idea of domain and range is not a new one to us, but looking at these three relations up here, two of them are functions and one of them is a relation. You could pause the video right now and test your knowledge on that. But we have a function in the first two examples and a relation in the third example. So as we talk domain, the domain of the first function you can see in this diagram of what we could call f of x, it looks like. Based on this closed circle and this open circle, our domain will be all values between -1 and +4, not including +4. Okay, of course, the domain is the x values. Common mistake is to use -5 and 0 there, but those have to do with range values, outputs. The range of f of x refers to the highest and lowest outputs. And in this case, we have a lowest output of -5 all the way up to a highest output of 4. Now, the 4 that I'm referring to is not the 4 that we looked at here with the domain. It is this 4 right here, which is the highest output yielded by this function. So this function goes from a -5 all the way up to a +4. If you'd like to, you can pause the video at this point and continue. I'm just going to keep rolling. So the domain here of what I'll just call y ends up being all values where x is greater than or equal to 4. The range for y is all values greater than or equal to 0. Okay, domain and range for the last function, I'm going to call it g of x, just to give it a name, is going to be from, oh boy, I gotta count, 1, 2, 3, 4, -5 inclusive, all the way over to 5 inclusive. And the range for g of x, it looks like is also the same, -5 to 5. And with the center circled at 0, that would make sense. Okay, that's a little bit of a review of domain and range evaluated from the graph of a function or relation. Let's move to the next topic. So in a previous lesson, we talked about determining whether a relation is a function. We can do this relatively quickly by also doing what's called a vertical line test, executing this idea that a relation is a function if and only if no vertical line intersects the graph at more than one point. Simply said, if I draw a vertical line and it crosses the function more than once, it is not a function. Well, I shouldn't have called it a function in the first place. So as I draw a vertical line, in this case, you can see this red dotted line that crosses the function, intersects it at two different points. That means that for this function, let's call it f of x, f of, what would that be, 1, 2, 3, equals -1, and f of 3 equals +3. Right? You see these outputs? I'm estimating, of course. But that's not possible, right? For a function, we can't have two outputs yielded by the same input. So this would not be a vertical, or not be a function. So it fails the vertical line test. Fails the vertical line test. Therefore, not a function. Okay, in the case of the second graph here, you can see no matter where I draw this vertical line, it would only cross the graph at one given point anywhere we were to place that. Therefore, this function passes the vertical line test. Therefore, it is a function. Okay, and I don't have a name for the function. I'm going to call it f of x, at least so I can put a name to it. F of x is a function in that case. That is obviously very useful regardless of the situation. So if you're asked to determine whether or not a relation is a function based on its graph, vertical line test should be your first step. Okay, let's keep moving. Okay, our next topic of discussion is determining where a function is increasing, decreasing, or constant. So a function is increasing if it is going up from left to right, decreasing if it's going down from left to right, and constant if it is not increasing or decreasing. Therefore, I'm just going to sketch on each of these graphs the portions that are decreasing. Okay, I see the decreasing portion in the first graph. Therefore, this graph is decreasing on the interval. We're going to do an open interval. It's never decreasing at an endpoint. From -2, of course, these are the x values for which this is true. It is decreasing on this interval from -2 to 0. Okay, the next graph isn't decreasing at all. So we would note not applicable in that situation. And in the third graph, it looks like my function is decreasing. Oops, went a little too far there. On this interval from -1 to 1. Notice how the graph is decreasing from left to right on that interval. Therefore, I could say from -1 to 1, that function is decreasing. I would like for you to try increasing and then come back and check my work. Okay, this first function is increasing. It is increasing from 2 to 4 on that open interval. The second function is increasing on the entire interval. Okay, therefore, since x cubed, its domain is all real numbers, it would be increasing from -infinity to +infinity. And you could just write all real numbers for x. Okay, and the third function is increasing from -infinity up to -1, as well as from 1 to infinity. Okay, again, go ahead, pause your video, and determine where these functions are constant. Okay, the first function is constant, as you can see, horizontal line from 0 to 2, and the others are not constant on any part of their interval or domain. That's the idea of increasing, decreasing, or constant functions. Let's move to the next topic. The next topic that we're going to cover relates to relative extrema. Relative extrema is a real fancy name for, is it a peak or a valley? And now a peak is considered a relative maxima. Okay, so a maximum in a specific window. So if I were to zoom in on this part of the graph, I would notice that there is a max value there. It's called a relative max, or could be called a local max. And of course, that would be happening at this location as well. So I could say that there'd be a relative max at B, x equals B, and x equals D. Whereas there's a relative minimum, or a local minimum, blue isn't the best color there, at x equals A and x equals C. So I could say there are local, this would get you full credit, minimum at x equals A and x equals C. There are local maximums at x equals B and x equals D. So if you would, you can pause the video right here and determine where the local minimum and local maximum values are on the second function. Okay, I'm going to write this out a little bit more formally. I didn't go into enough detail over here in the first example, but I am going to here. Therefore, I'm going to say that f of x has a local max. You could also use the word relative max here, of 2 at x equals -1. A little bit more specific now with the output at that local maximum. F of x has a local min. Totally fine if you abbreviate with max and min instead of maximum or minimum or maxima or minima, but it has a local minimum of -2 at x equals 1. Now a function could have multiple local maxes like you see in the first example. It could have 0 local maxes. Okay, an example where a function might have 0 local maxes would be a quadratic function. That has no local maxes. Okay, but depending on what the polynomial function looks like, it will vary from case to case. All right, let's move to the next topic. Okay, our next topic is the idea of even and odd functions. If a function is not even and not odd, then we just call it neither. The definition of an even function is a function is even if for each x in the domain of f of x is equal to f of -x. All that means is that the outputs for 1 and -1 would be the same, or 2 and -2 would be the same, or 3 and -3. So specifically, let's look at this first example here. Okay, if I plug in an x, I get y. If I plug in a -x, I also get y. All that means is that I've got a symmetry along this y-axis. So even functions are also said to have y-axis symmetry. It's like a perfect reflection across the y-axis. You can see that in both of these examples. Right? Here's example number 1. Here's example number 2. Another function, which you may have seen before, that is an even function, is cosine. This is a trigonometric function. Not my best graph, but you can see that if I plugged in, let's say, pi over 4, and I plugged in -pi over 4, that their outputs have the exact same y value. So it's a perfect reflection across the y-axis. Okay, let's shift our attention over to the odd function, which is said to have origin symmetry. Okay, an odd function, let's zoom back out here. A function is odd if for each x in the domain of f of x is equal to -f of x. Notice the slight difference between even and odd when it comes to the right side of that equation. Okay, this is the opposite of f of x. Therefore, if I look at these sketches here, you can see that if I plug in an x, I get y. If I plug in a -x, I get -y. So if I plugged in, let's say, 1, and I got 2, if I plug in a -1, I should get a -2. Okay, now, the reason this is called origin symmetry is because if I were to rotate this point about the origin 180 degrees, and it wasn't a perfect rotation, but if I were to rotate that 180 degrees, it would match up with the other point. Okay, and likewise here, you can see in the second example, g of x is x cubed minus x. If I took this point right here, I'm not sure what it is, and I rotated it 180 degrees, it would match up perfectly there. Likewise with these, that has origin symmetry. And the reason why is because when I rotate it 180 degrees, that's the origin is the center of rotation. Okay, so graphically, I can show you another odd function. The function, this was cosine x. I'm going to show you, let's see, how about tangent x? You may not remember the graph of tangent, but it is an odd function. The graph of tangent x between negative pi over 2 and pi over 2 looks like this. It's got this cool symmetry to it. You may not remember this, or maybe you do, but the tangent of pi over 4 is 1, and the tangent of negative pi over 4 is negative 1. Oops, there we go. Wow, that was poorly sketched. Let me try that again. Sorry, guys. Negative 1. That's better. So it's a perfect rotation. If I took the graph and I spun it, right? If I pinned it right here and I slapped it, right? Like I was playing Wheel of Fortune and I just spun that thing and it rotated some amount of 180, either 180 twice, 3 times, 4 times, 5 times, 6 times, whatever, it would land right back on itself. Okay, so if I look at this unknown function and I just looked at it, it kind of looks odd, doesn't it? But the problem is if I rotate the function about the origin, I have an issue, right? So if I were to, so in essence, this is neither. It's neither even nor odd. Clearly I can tell it's not even, right? Because if I reflected it across the y-axis, this part of the graph would look like this, and it doesn't match up, right? And this part of the graph, if I reflected it across the y-axis, would look like that. So the graph isn't matching up to be even. It's also not going to match up to be odd. And you can see it in a couple of different ways. Here, this is the point 1, 0. So in an odd function, if I have an odd function, then negative 1 should yield negative 0, which should put a point here. And that clearly doesn't exist. So this function is not odd either. Therefore, it's neither. All right, on the next slide, what I want to do is I want to show you how to determine whether or not a function is even, odd, or neither using algebra and not the graph. So let's go ahead and jump ahead. Okay, so let's take a look at this slide. To determine if a function is even, odd, or neither algebraically, we must show one of the following is true. F of x is even if f of x is equal to f of negative x. F of x is odd if f of x is equal to negative f of x. And f of x is neither even nor odd if both the above statements are false. So let's take and look here real quick at this first example. Okay, so here's f of x. I know what f of x is. I'm going to plug in a negative x into that function. Therefore, f of negative x will equal negative x inserted everywhere you see an x. Okay, now let's simplify that right side. If I cube a negative x, I get negative x cubed, because negative 1 cubed is negative 1, and x cubed is x cubed. Okay, likewise, in the second portion, if I distribute a negative onto a negative, I get a positive x. Well, clearly this is not equal to f of x, right? You can tell, right? The sign here was positive, the sign here was negative, and that doesn't match up. So at this point, I know that it's not even. So it can either be odd or it can be neither. Now I'm going to take a next step, and typically your next step should be, let's take out a negative 1. Okay, if I take a negative 1 out, I get x cubed. If I take a negative 1 out of the second term, I get a negative x. And what's cool is I've got a negative 1, and then I've got f of x. So this is negative f of x. And based on this idea of f of x being odd, if f of x is equal to negative f of x, which I've shown algebraically, I've actually just found a mistake in my notes. Sorry guys, let me fix this real quick. There should be a negative in here. So it should say if f of negative x is equal to negative f of x. Okay, we can change that on the last slide as well. But since I've shown that right here, f of negative x is equal to negative f of x, then f of x is odd. So if I were to graph that, that should have origin symmetry. Okay, let's look at g of x. All right, let's go ahead and let's plug in a negative x, g of negative x, and I'm going to actually reformulate this just slightly. I'm going to write this as the 4 times the cube root of x squared. Okay, let me just rewrite g of x, and then we'll do the algebra on it. Okay, so I've reformulated it. That's a rule of exponents there. This is x squared to the 1/3 power. Okay, so x squared to the 1/3 power is equivalent to x to the 2/3 power, which is also equal to the cube root of x squared. Okay, so now what I'm going to do is g of negative x, I want to know what that equals. Take 4 times the cube root of negative x squared. Well, what happens when I square negative x is I get positive x. So I get 4 cube root of x squared. And reformulating that just back to where it was, that'd be 4x to the 2/3, which is actually equivalent to g of x. So now I've shown that g of negative x is equal to g of x, which means that g of x is even. Outstanding. Okay, last item for the notes for today. X cubed plus 3. Let's take a look at that. So h of negative x is equal to negative x cubed plus 2, which if I cube a negative x cubed, or a negative x, I get negative x cubed plus 2. Now that's not equal to h of x. Since that's not equal to h of x, we know it's not even. Therefore, I'm going to take out a negative 1. That leaves me with x cubed minus 2 on the inside. And this is not equal to negative f of x, because this is not f of x right here. Okay, so since it is not equal to h of x and it's not equal to negative h of x, it's not odd. Therefore, h of x is neither odd nor even. All right, guys, that is lesson 1C. If you got any questions, shoot me a message. Otherwise, we'll see you in the next one.